Hi, ladies and gentlemen. I welcome you to another series of our lectures, and today we'll focus on looking at electrochemistry part 2. Okay, in electrochemistry part 2, we'll focus mostly on what you normally refer to as the Nest's equation. Okay, so we have the Nest's equation. Now, the Nest's equation is good for non-standard conditions. Last time we looked at the cell potential based on standard conditions, right? And those conditions include the temperature will be equals to 25 degrees, then the concentration, meaning molarity, is equals to 1.0 molar, and the pressure is equals to 1 atmosphere. Okay, so when we're talking about the standard, right, cell potential, meaning it was the potential was carried out on standard conditions, which is 25 degrees temperature, 1 molar concentration, and 1 atmosphere. But if you look at the next equation, helps us calculate the voltage of the cell on the conditions that are non-standard. So the next equation works with the non-standard condition. So what it means that the concentration want to be equals to 1 molar and the pressure want to be equals to 1 atmosphere. Okay, so now what you have here is basically what you normally refer to as the next equation. Now what we'll do is that in the next equation you have some parameters that needs to define. For example, you have E cell, meaning the potential at non-standard conditions, right? Sorry, my writing is very bad. Then this is the standard cell potential, more or less like the one that we were discussing in our previous lectures. Then now we have constant in this value. So what you have, the first one we have F is a Faraday, which is the Faraday constant, normally given by 96 485, and sometimes it is normally rounded off to just 96 500 coulombs per mole. Then you have the R value, which is given by this. The R value you're talking about is a gas constant, which is given by 8.314 joules per mole per Kelvin. Then you have T. T is the temperature in kelvins. Then you know that temperature in Kelvin is equals to 273 times temperature in degrees. So what you do is that, for example, if you multiply, sorry, for example, if you have you add 25 degrees, you have 273 plus 25, it's giving you 298 kelvins. So this is how you get the temperature. So this is the relationship that exists between a Kelvin and a degree. So you just have to add 273 to a degree, then it gives you the temperature in kelvins. So now what you get here is, for example, in our next slide, you have this parameter here, right? This is the chemical equation. Now then you understand that in the next equation, there is this parameter here that is coming from here. So the next thing that we do is how we generate this parameter. Okay, stay with me. So that parameter is normally referred to as the reaction quotient. Now the reaction quotient Q is given by the concentration of the product raised to the mole divided by concentration of the reactants raised to the mole of the reactants. Then from this equation you understand that this small letter A, B, C, sorry, D is supposed to be here, actually gives you the number of moles of species. So this is what you have that have been raised to the power. So now in this particular case, what you get is that these are products, right? Then these are reactants. Then we can use this equation, which will be equals to uh, concentration of C raised to the power C, because this is a constant mole, times concentration of D, capital D raised to the power small d, divided by concentration of A raised to the power small a and concentration of B raised to the power B. And this is how we determine the reaction quotient. It's very simple and straightforward. So what you get here is that, because you normally know that the easiest way to write the next equation is you get Q, but the responsibility that you have is basically on how to derive or how to come about Q, and this is just what I'm showing you. This is what I've been doing. Okay, let's simplify the next is equation. Now, from our previous slide, we understand that the next equation is of E cell is equals to E cell, E standard minus 2.303 RT divided by NF, then log Q. Okay, so what we want to do is to simplify the Ness's equation, right? So that we can get an easy version that we can be working with our calculations. So now how do we do that? We just substitute all the constants. So we know we have the F constant, we have the R constant, and we have the T constant. So we can substitute for R, T, and F, so that it gives us a simplified versions of the next equation. So from this, what you get, this will be to E cell minus 2.303 open bracket. The value for R is this, so we substitute 8.314 joules per mole per Kelvin times T, the temperature, which is open bracket 298 Kelvin, then divide by N times the Faraday constant, which is 96,485 coulomb per mole. Okay, then we can add this parameter log Q. Perfect. Then from here, what we do is that when you simplify, when you multiply this number by this number by this number and divide by this number, what you get is 0.0592 divided by N, then minus standard cell potential, then you have cell potential. Then let's cancel the units. We have to the more here and more will cancel. Kelvins here and the kelvins will cancel. So now what will remain as units in next equation is, let me just put them all together. You have open bracket, you have joule per coulomb, which is joule per coulomb as our unit, then log Q. So this gives you a simplified version of the next equation. But one thing to understand is that T here is equals to 25 degrees, which is equals to 298 Kelvin. So this equation is only true at 25 degrees. If you change the concentration, it also increases because the parameter here will increase. All right, solving for units. From our equation, we have E cell is equals to E potential minus 0.0592 divided by N, then JC log Q. Then from the previous slides, we know that 1 volt is equivalent to 1 coulomb per mole. So we can substitute this value here. So what we have now is C is equals to standard cell potential minus 0.0592 V divided by N log Q. From our previous calculations, we discovered this is normally given as voltage. So if this is voltage and this is voltage, then we can have our final answer for each cell. The units will also be volts. Okay, so that's how we sort out our units for next is equation. I think the most important thing is that once you establish a concept or a fact, the next step to do is to work out an example. So I would like you to pay particular attention at this point and go through this example with me. Okay, the question reads, calculate the potential of the cell for this reaction here. So you have this reaction over here. So what we're trying to do is to calculate the cell of this reaction here. Then we understood that from a previous equation that this gives us the simplified version of the next equation. So what we need to do first is what we want to determine is this parameter here, which is the potential of the cell at non, so you have at non-standard condition. All right. So the job that we have to do is to establish or to calculate the cell potential at non-standard condition. Then this we can easily calculate because we calculate this value based on the standard reduction potential like we've done in the previous examples. Then we can determine the number of electrons, meaning we can easily determine N, then we can also determine Q, and that basically makes our life very, very simple. So now here is the thing. Before we go to, there are new parameters that are appearing here, which I would like to go through with you so that you get an understanding on how you write this. Now, if you look at the standard, right, reduction potentials, right? Standard reduction potential. Now, you understand that from our previous, in part one, we did calculations based on the standard reduction potentials. Now, we say that most of the reaction in a cell are normally given as reduction reaction. So, for example, if you have zinc plus 2 electrons giving you uh, zinc solid, then you have copper 2 plus 2 giving you copper solid. So when it comes to writing the standard reduction potential for this reaction, it will be E, like E0. Zero means standard conditions. Okay, where we? Okay, I think we're here. This is okay. We can just write this. This is copper. Sorry, zinc. Then this is copper 2. Okay, like this. So when it comes to writing the E0 for zinc, it will be 2 plus divided by this, which is basically given by minus 0.76 volts. Same applies for copper. It will be E0, then copper 2 plus divided by copper, then equals to plus 0.34 volts. So This is what we get as our standard reduction potential. So all standard reduction potential can written in this notation. So you can use this notation to represent all standard reduction potential in form of a reduction reaction. Now remember this, the reduction standard potential gives you the degree in which a compound can undergo reduction reaction. Okay, I think I have expanded on the notation, so we will not spend a lot of time on the notation. Okay, so this is what I was talking about. So this is how these notations actually come about or emerge, as I was showing you in the previous reactions. Now, the other key important thing is to determine what is N. Then you know that N is basically the number of electrons. So now what we do here is that we can divide our equation into two. So you have a solid here and an aqueous. So what you get is that you have zinc solid is equals to zinc 2, right? Then we come to the second equation. We have copper 2 is equals to copper solid. In our previous slide, when we defined what oxidation is, we said oxidation, there's increase in the charge. So meaning you are moving from the charge 0 here to +2. Now, how do you balance up the charges on both sides of the equation? Is that you add a negative charge where there is a positive charge. So for example, there's a 0 here, there's a positive charge. So we add the negative charge where there's a positive charge. So since there are two positive charges here, we add 2 electrons. Then we come to this equation. This is 0 and this is +2. The same rule still applies. We add a negative, so we add electrons to where there's a more positive charge. Now, since there are two positive charges here, we also add 2 electrons like this. So now what we notice is that from this equation, right, from this equation and this equation, the number of electrons are, there's 2 here, there's 2. So meaning what it means that there's 2 here and there's 2. So what it means that this is undergoing oxidation and this is undergoing reduction. Okay, reduction. All right. So if we define oxidation, oxidation is a loss of electrons, which is this, 2 electrons have been lost. Then reduction is a gain of electrons and 2 electrons have been lost. So since there are 2 electrons here, there are 2 electrons here, so they are all balanced. So what we can conclude that N is equals to 2. All right, standard cell potential. Now, from our previous slide, we calculated standard potential. We know that the standard reduction potential is equals to standard potential for the reduction reaction and standard potential for the oxidation reaction. Then from our previous slide, we understood that this is undergoing oxidation, zinc. Then the value for zinc is minus 0.7. The value for zinc E0 is equals to minus 0.76 volts. Then for this E0 is equals to which is this, plus 0.34 volts. So we can substitute in our equation. So from here we know that in other ways, or in simpler terms, you can write this as E0 is equals to E, which is basically copper, minus E, which is basically zinc, right? So this will be equals to plus 0.34 volts plus minus 0.76 volts, which is basically plus 1.10 volts. That's the standard cell potential. Now let's calculate the cell potential at non-standard condition. And by now we know that that can only be brought to reality by using the Nest's equation, which is this. All right. So in the next equation, we also have a parameter that we normally refer to as Q. Okay, so Q Q, right? Q is equals to concentration of the product raised to the mole divided by concentration of the reactants raised to the mole. So now, how do we achieve this? Let's go to our equation. Let me use this slide to try to solve what we have here. So that because we have an equation here, then we want to establish. But here is one point that you need to master about the reaction quotient. So what you get is that only liquids, meaning aqueous and gaseous states, are included in Q. Solids are skipped. So you skip the solids and you only use the liquid or an aqueous and a gas. So let's write the reaction quotient for this. So you have Q will be equals to concentration of zinc. Since there's one here, so it will be raised to the power 1. So it's anything raised to the power 1 by 1 is that thing. Then you go to, okay, sorry. I have, okay. So what you get is Q is equals to product divided by reactants. All right. Then the key point, like I have mentioned, only liquids and gases are included, no solids. So from this point, we can say okay. So from this point, we can say Q is equals to the concentration of the products, which is copper, times the concentration of zinc 2 plus divided by the concentration of zinc, then divide by times the concentration of copper 2 plus. Now, like we've said, no solid, so meaning there's a solid here, it's out, and the solid here, it's out. So you can cancel also this, and this. So what remains are only liquid. So in short, what you have, this is equals to concentration of zinc 2 plus divided by concentration of copper 2 plus. All right, this is not Rabi. Okay. Okay, so from here we know that Q. Okay, just give me a minute. Okay, let me wrap this. Okay, so if we get here now, from what we've established, we know that Q will be equals to concentration Q will be equals to the concentration. Let's say Q will basically equals to concentration of zinc 2 plus divided by uh, concentration of copper 2 plus. Then from here we can substitute in the values. So what we get is that we know that the concentration of zinc 2 plus it is 0.25 divided by the concentration of copper 2 plus is 0.15. So from here we can substitute in the next equation now, because we know that E cell will be equals to, we calculated the cell potential, the standard cell potential, which is plus 1.1 volts minus, then we know the number of electrons are 2, so it's 0.59 divided by 2, then log 0.25 divided by 0.15, like that. Then when you simplify this value, what you get is plus 1.094 volts as your answer. Then from here, you know that 1.9 volts is greater than E. So meaning this is a forward reaction, or it is a spontaneous reaction. Okay, so that's how you calculate the cell potential for next equation. Okay, the cell potential can also use to be determine the pH. Just a quick review what pH is. In logarithm, pH is basically log minus log of hydrogen concentration. So in short, when you're talking about pH, pH just tells you about the amount of hydrogen concentration in the solution. Then what you have is that pH scale ranges from 1 to 7 to 14. So anything above 7 is basic, then below 7 is acidic, and at 7 is neutral. So now our responsibility is to look on how you can substitute, so how you can calculate for the pH. On that one, we'll go through together. Okay, the question: the potential of the cell from the reaction. So this is a reaction. Is this? So in this particular point, now from this equation, we know that this value is 0.54 volts. Perfect. Find its pH given that the cell potential of zinc is minus 0.76. We've already established that. And the cell potential of hydrogen is 0.0. So this hydrogen is moist. What we talk about is the She, meaning the standard hydrogen electrolyte. So now, how do we solve for the pH of this solution? Then from here, the first step is to calculate the cell potential, right? The standard cell potential. So E and 0 will be equals to E reduction minus E oxidation. Then if we look at the value, this is 0 and this is minus, so this is great. So in short, this will undergo reduction. So from here, what you get, this is will be equals to 0.00 minus 0.76. Then this is equals to 0.76 volts. So what it means now is this is 0 is equals to 0.76 volts. All right. So we go in step by step. Then the second step is let's determine the number of electrons that are involved in the reaction. Okay. With the electrons, let's look at the equation. From the equation is we have zinc solid giving you zinc 2, right? This is what we are seeing here, okay? Then from the other side, we have 2 hydrogen plus giving you hydrogen gas. So we use the same concept. There are 2 positive charge here, so you add plus 2 electrons. There are 2 hydrogens here, meaning when you multiply 2 by plus, they give you 2 positive charge. So meaning you what to do is you add the plus 2 to balance up. So in short, 2 electrons, 2 electrons. So meaning N is equal to 2. So from our equation, this N, so from our equation, this N is equals to 2. All right, let's work out the Q value. The Q value will be equals to the product. There's the concentration of zinc. Then P is a gas, so it's going to be pressure. So times the pressure of hydrogen divided by the concentration of zinc solid times hydrogen plus. Now, if you look at the value of hydrogen, hydrogen has a number of moles 2. Like we've said in the previous examples, is that when you have a mole, it is raised to the power. So since there's a mole 2 here, so it will be raised to the power 2 over there. Then when we look at our previous concept, we said solids do not appear in the reaction quotient, so this will be out. So now what we get is this solid will be out. So our equation will basically become this. Then hydrogen gas divided by the concentration of hydrogen 2. All right, perfect. So from our equation, we know that that's 1, and this is 1 divided by 2. So this is basically equals to 1 divided by the concentration of hydrogen 2. So when we substitute our equation, what we get basically is 0.54 is equals to 0.76 minus 0.0592 divided by 2, then log 1 divided by hydrogen concentration. Now, like we've said, is definitely defined by the amount of hydrogen ions that are present in the solution. So in this short, this parameter will help us calculate the pH. So okay, now let's focus on this parameter only for now. So from here, what you get is that you have log 1 divided by hydrogen concentration. Let's do some mathematical equation. So you know that anything, let's say divide by x is equals to x minus 1. So when we convert this into this parameter, this will be equals to log hydrogen concentration 2 times minus 1, which is basically equals to log hydrogen concentration minus 2. Okay. Then from mathematics, you also understand that log x y is equals to y log x. So if we convert our equation to this, what we get, this will be equals to minus 2 log hydrogen concentration. Then from here, okay, let me get space. Okay, let me use this. Then from here, what you get is that let's get this here, right? So you have minus log hydrogen concentration, which is basically, then from here you know that pH is equals to minus log hydrogen concentration. So we need to convert to this parameter. And how do we do that? We say minus 2 log hydrogen concentration is equals to 2 open brackets minus log hydrogen concentration. Then if you look at this is equals to pH, so in short this will be equals to 2 pH as your answer. Then from here, what we get is that where's my rubber? Okay. Okay, now that we've solved for that parameter, then let's get back to our next equation. So because you know, like we have is cell is equals to E standard cell minus 0.0592 divided by n log q, right? So if we substitute in all our variables, we understood that from our equation, we know that E cell is equals to 0.54 volts. E standard cell is equals to 0.76 volts. N is equals to 2 and log Q is equals to 2 pH from what we calculated. Then we can substitute in the values. Let's write the new next is equation. So from here we have 0.54 volts equals to 0.76 volts minus 0.0592 divided by 2 pH. So this 2 and this 2 will cancel. So what you get is 0.54 V equals to 0.76 V minus 0.0592 pH. Then from here you can solve for pH, right? You can solve for pH, and what you discover after you solve for pH is that your value will basically be equals to 3.72. Okay, Gibbs free energy. Okay, Gibbs free energy just gives you the energy that is generated in the redox reaction. Then Gibbs free energy is calculated by change in Gibbs is equals to minus NFE. So you know that F is Faraday constant, then E is the cell potential. Okay, so from here you know that if the reaction is spontaneous, delta change is less than 0. Delta G. If the reaction is equilibrium, delta G is equals to 0. If the reaction is at non-equilibrium, then delta G is equals to greater than 0. So these are actually opposite to cell potential, because for a spontaneous reaction, cell potential is greater than 0, then this is the same, then E is less than 0 for the spontaneous. So basically what you have, that the change in G is opposite to the cell potential. All right, let's look at an example. Calculate the standard the standard Gibbs free energy change, which is that at 25 degrees for the following reaction from the standard electrolyte potentials. Okay, so from here, what you get is that if you use the standard reduction potential, which is for this will be 0.13, then for chromium it will be minus 0.73. So in short, this is undergoing reduction and this is undergoing oxidation. Then let's determine the number of electron transferred, right? We split the reaction into half reactions. So the first reaction is we have SN4 plus giving us S2 plus. Then the other one we have chromium giving us chromium 3 ion. Now what we say is that we calculate the positive charge. Where there's a lot of positive charge, you add the number of electrons to reduce the positive charge. So if you see there's plus 2 plus 4, so we add 2 electrons here. There's 0, there's plus 3, so we add 3 electrons here. Now there's 2 electrons transfer here, there's 3 electrons transfer. Now how do you balance up the equation? So what to do is we find the common lowest multiple or common lowest product of 3 and 6. So in short, how you can get that is you multiply this equation by 3 and this equation by 2. So what it gives is that this will be equals to 2s4 plus 6 electrons equals to 2, like this, right? Then you have for this equation, if you multiply 3, sorry, if you this is let me try to, I think I made a mistake. This is not okay. We get back to this one. We are multiplying this equation by 3, right? So it will be 3s24 plus 3 times 2 gives you 6 electrons, giving you then 3 times this you get 3sn2 plus. Then for this equation you multiply by 2, which means you get 2 chromium, giving you 2 chromium 3 plus 6 electrons. So the number of electrons are balanced. There's 6 here, there's 6. So what it means is that n is equals to 6. This is what you get here. N is equals to 6 for that reaction. Okay. So from what we know is that change in energy is equals to NF and E cell. So we know the number of electrons is 6, then we know what the Faraday constant is, then we can calculate the standard cell potential, which is given by standard reduction divided by standard oxidation reaction. Then when we fuse in the values, we discover to get minus 0.4 times 10 to the power 5. So what we get that since this is less than 0, so this is a spontaneous reaction. Okay, let's look at this electrolytic cell. In these cells, non-spontaneous chemical reactions are forced to occur by an input of an electric current. So what we have is that you have a non-spontaneous reaction that is driven by an external electric current. And this process is normally called as electrolysis. Uh, the reaction is reluctant to take place. So electricity is added so that you cause the reaction to take place because this is as a result of a non-spontaneous reaction. Okay, electrolytic cell consists of containers for which the material with electrodes are immersed in this reaction material and connected to the source of DC. So you have two electrolytes type, they can either be an innate or an active. So this gives us so what you get is that the principle of electrolysis are the same as those that apply to electrochemical cell carried out in galvanic cell. But there are some differences that are observed that we are yet to discover as we proceed. Okay, this is how an electrolytic cell looks like. As you can see, both the electrolytes are immersed in one solution. In this case, is sodium chloride. Then you have an external source of power. Then there are also two electrodes. There's a cathode, which is negatively charged, and there's an anode, which is positively charged. Now, pay attention to these details because this becomes very key when we start looking at the differences between an electrolytic cell and a galvanic cell. So now, electrolytic cell like galvanic cell are composed of two half cells. One is a reaction half cells and the other one is an oxidation half cells. So in those cases, they are quite similar. Then the direction of flow of electrons, however, may be reversed from the direction of a spontaneous reaction. So now what you get here is that in an electrolytic cell, the transfer of electrons or the flow of electrons is opposite from a galvanic cell. The reason being a spontaneous reaction will go in the forward direction and which is a spontaneous reaction. Then for electrolytic cell will go to the backwards because it is forced by an electric current. Then in both cases, both the cathode and the anode remain the same, where reduction takes place at the cathode and oxidation takes place at the anode. So these are some of the similarities that you experience or you get to see. Then because of the direction of both half reactions have been reversed, the sign but not the magnitude of the potential have been reversed. So in short, this is a cathode in an electrolytic cell, but this and it's a negative charge, but it will be a positive charge when it gets to a galvanic cell. We'll get to see that when you have two diagrams that we compare both the cells together. Okay, so this gives you a pictorial representation of an electrolytic cell. So what you have basically is you have a source of DC over here. So this is DC, right? Then the electrons are moving from an innate electrolyte, which is the anode, to another innate electrolyte, which is a cathode. So these arrows is showing you the directions of electrons. Then inside here, those two electrons are immersed in a molten sodium chloride. Now, the reason why we move sodium chloride is because it's a medium that is able to transfer electricity from one point to the other so that you have a complete circuit. Because just imagine if electrons was to move from here and get here, then there's no connection between these two. Then that's the end of the reaction. So what to do is to complete or to make the reaction and have a complete circuit, you add a molten sodium chloride that can allow conduction of electricity from this point to that point. Okay, consider electrolysis of molten lead to bromide, which is written like this. Now, ion involved, this is what you get. So you have lead giving you lead 2 plus bromide minus. So these are two like this. Okay, so what you get at the anode, there's a bromide ion. At the cathode, there's lead ion. Then now, what you have at which ion are preferred discharge at the anode and the cathode. So there's this at the anode and this at the cathode. Then oxidation reaction, this undergoes oxidation reaction. So meaning bromine. So now what we get is that, for example, in our previous example, if we say we have M plus giving you M. So how do you balance this? You add electrons to the compound that has more positive charge. So in this case, you add an electron to plus 1 electron. But in this case, you have 0 and you have minus 2. So how do you balance up this? You subtract 2 electrons to balance up on the side. That's where the negative sign is coming from. Then this gives you the overall reaction, because what you get, you have bromide ion giving you bromide gas, then lead ion giving you lead metal. Okay, electrolysis of water. So in this case is that water is undergoing oxidation and the same water is undergoing reduction. And how is that achieved? You add an external EMF, which is a battery. So when you add an external EMF, so what you have is that you connect to. So hydrogen gas is collected in this bubble, in this container, and oxygen gas is collected in this container. Then you can observe bubbles forming. Bubbles are telling you the formation or evolution of a gas, and this is what you get. So what you have is that you have two half reaction. So in the half reaction, oxidation reaction, water molecule produces oxygen and the hydrogen ions. Then in the reduction reaction, water molecules produce hydrogen gas plus hydroxyl ion. So when you write the net equation of this and you balance up, you actually discover two molecules of water will give you two hydrogen gases and two hydrogen oxygen gas. Okay, what are the similarities and differences between a galvanic cell and an electrolytic cell? Electrolytic cells are very similar to galvanic, which is also known as voltaic cells, in the sense that both requires a set bridge. Okay, this one we need to cancel it because only one requires a sort of bridge, and that's a galvanic cell. Then both have the cathode and an anode side, and both have a consistent flow of electrons from an anode to the cathode. Then, however, there are also striking differences between the two cells. The main differences are outlined as below. Electrolytic cell, which is a galvanic cell, or electrochemical cell, which is a galvanic cell, versus an electrolytic cell. Galvanic cell convert chemical energy into electrical energy because it's a spontaneous reaction. So what it is that the reaction will take place on its own. So chemical energy will be converted into electrical energy. But for electrolysis, it's a non-spontaneous reaction. So meaning electrical energy will be converted into, because you have an external source of DC. So that external source of DC will be a source of electrical energy, which drives the reaction until chemical energy is produced. So redox reaction is spontaneous and responsible for the production of chemical energy. The redox reaction is non-spontaneous. It's not spontaneous, and electrical energy has to be supplied to initiate the reaction. So Half cells are set up in a different container, so meaning they are put in a different container, being separated through a salt bridge or a porous partition. Both electrodes are placed in the same containers. That's for electrolytic cell. Then over here, the anode is negative and the cathode is positive electrode. The reaction at the anode is oxidation and the anode oxide cathode is reduction. So it's the same thing. The only difference is that the anode here is positive and the cathode here is negative. And the reaction at the anode is the is oxidation. So same applies in all cases, it's oxidation. And the reaction at the cathode is the reduction. So it's the same thing. Electrons are supplied by a species getting oxidized. They move from the anode to the cathode in an external circuit. Then external battery supplies the electrons. Here the electrons are supplied by the reaction species, the reacting species. Here the electrons are supplied by a battery. They can enter through the anode and come out through, so they can enter through the cathode and come out through the anode. Okay, so this gives you two examples of the cell. So you have a galvanic cell and an electric cell. So galvanic cell is not spontaneous. So what you put is a voltmeter to measure voltage. For an electric cell, it's a non-spontaneous. So you put a battery to drive the reaction. Then you can see there are two containers here. There's one container there and the other container. But all the electrolytes here are mixed in one container. Then in this side, the anode is positive and the anode here is negative. The cathode is positive and the cathode here is negative. So you have non-spontaneous reaction and a spontaneous reaction. So this does not require any external source of voltage and this requires a source of voltage. Okay, so there are some of the differences that you can look up and understand this a bit more. The key point is that this is a non-redox reaction and this is a redox reaction. Okay, Faraday laws of electrolysis. It states that the amount of material deposited or evolved at an electrode is proportional to the electric charge passing through the same solution. So the electric charge that you pass through the solution initiates how much or tells you how much of your metal or material will be deposited on the electrode. Okay, let's look at an example. So you have charge is equals to time, so it's equals to current divided times time. Charge is equals to current times time. Okay, if 306 coulombs of a charge is passed through a solution of copper nitrate, right? Okay, so copper nitrate, you know, it ionizes like this, so it gives you copper 2 plus 2. Okay, let me write it here. Copper nitrate giving you copper 2 plus 2 nitrate ions. So meaning there's 2 here plus 2, so meaning N is equals to 2. So in short, what you get is that the mole ratios between copper and N is 1 to 2. So what it means that 1 mole of copper is produced by 2 moles of by 2 moles of electrons. So this is moles of electrons. Okay, so now we can discover of moles of an electron using the charge that is being passed. So now, how do we determine that? It's easy. If you look at the Faraday constant, F says F is equals to 9 6 500 coulomb per mole. So in other terms, we're saying 1 mole is equals to 96,500 coulombs. Now, suppose you have this number of coulombs. How many moles are you going to get? So you get 306 coulombs. So then you say equals. So this is x. So when you cross multiply, this will be equals to 1 mole times 300 coulombs divided by 96,500 coulombs. So this coulomb and this coulomb will cancel. So what you get as your moles will be equals to 0.00317 moles. Now note that these moles are coming from the charge. So these are the moles of electrons. Okay, those moles are moles of an electron. So now how do we discover the moles of copper? It is easy. We look at the mole ratio, right? So you have copper times the number of electrons or moles of electrons. So from the moles of electrons, you have 1 copper is equivalent to 2 moles of electrons. So if you have 0.00317 moles of an electrons, how many copper moles are you going to have? So it's cross multiply. So it is 1 times 0.00317 mole divided by 2. And our answer basically is 0.00158 more of copper were deposited. Okay, the equation is similar. Now you had 306. This has multiplied by 2, so it's common sense. What you get is just multiply your answer by 2, and it gives you that. Okay, let's solve this. How long would it take to deposit this number of moles of metallic gold by electrolysis of this using this current? Okay, let's start with here. Let's start the oxidation number of gold. So if you look at gold, this is 0. Then what's the oxidation number of gold in that reaction? So from here, you know from the periodic table, the oxidation number of any group 1 element is +1, and the oxidation number of any group 7 element is -1. So now what you get is from here is +1 times 1, because there's only one of it, plus x, we don't know what the gold state is, and plus 4 times -1. So from here you have 1 plus x minus 4, which is equals to 0, because the charge of all of this molecule is equals to 0. So from here what you get is that x minus 3 is equals to 0, so x is equals to 3. So in short, the electron transfer n is equals to 3. So from here we can look at the relationship. So if we look at the mole ratios between gold, so let's do mole ratios, right? Gold and the number of electrons. What you get, this is 1, 2, 3. Then for gold, they are about 0.00235 moles against x, or cross multiply. So yes, x is equals to 3 times 0.00235. So 235 divided by 1, and our answer will be equals to 0.00705 moles. Okay, so now that we've established the number of moles that pass through that were emitted by God, then we can now determine the number of coulombs associated with this number of moles. We go to Faraday is equals to 96,500 coulomb per per mole. Now, 1 mole is equals to 96,500 coulomb. What about if you have 0.00705 moles? What did you get? So this is cross multiply. So this is x is equals to 0.00705 times 96,500 divide by 1, and the answer that you get is equal to 680 coulomb. Perfect. So these are the number of coulombs that pass through the electric charge. Then now, okay. So now from here, what you get is that, okay, let me rub this. Okay, now that you found the 680 coulombs, now how do we convert the coulombs to time? The answer is simple. Okay, the answer is basically simple. So how do you convert coulombs to charge? From our previous equation, we know that Q is equals to I times T. And what we are looking for is T. So T is equals to Q divided by I, which is basically equals to 680 coulombs divided by what's I is the current, which is 0.214 amps. Then from our equation, we know that 1 coulomb is equals to 1 amps per, 1 amp second. With this is because now to 680 amps second divided by 0.214 A. So this cancels, and this gives us our final time in first, which is 3179 seconds, which can convert it to 53 minutes. Okay, so you can solve this equation. They are quite similar. You can just solve them by yourself to just practice for practice purposes. Okay, application of electrolytic cell. You can use a Lenkrach cell. Now, a Lenkrach cell has so what you get, you have a cathode here, which is so you get a cathode here, which is magnesium oxide plus graphite, and an anode, which is zinc plus copper oxide. So this gives you an example that is used as a cell, or it is used as a battery. Then the other one that you get is rechargeable batteries, right? Rechargeable batteries are made both of a galvanic cell and a non-galvanic cell. For example, if you're using your phone, once you unplug your phone from power, it starts using a galvanic cell. So meaning it depends on a spontaneous reaction to supply electricity. But once you add it to power, then it becomes an electrolytic cell. So meaning the reverse of that now makes the phone to start charging. Okay, corrosion. Corrosion is when you have a spot that is exposed to air, and basically those are just one examples of uh, oxidation and reduction reaction. Okay, you can prevent corrosion by painting and attaching a sacrificial anode made of either zinc, aluminum, or alloy. Then a sacrificial alloy means it does not corrode and it can be replaced at any time. An ideal anode is innate or it's passive. so that the rate of corrosion is very slow. So these metals include aluminium, chromium, tin, nickel, essentially unreactive with air and okay, electrolysis in copper industry. Now, electrolysis is the method that's used to purify copper. So what you have here, a positive charge, that's where pure copper is collected, and the negative charge, that's where impure copper is normally collected. So one basic key component of electrolysis is separation of metal in an industry. All right, I think that's about it. I can end here. So I'll see you in the next video. Bye.